Chapter Well, this is page 674 from chapter 14. There are 3 paragraphs here. You can read those. That'll help understanding what activities are. These 3 paragraphs and this table 14.4. One time I gave an example of an activity that is the stoichiometric concentration versus the effective concentration for benzoic acid. Does anybody remember that? Benzoic acid. Dimerization. Does anybody remember dimerization or dimers? Benzoic acid dimers? No? Basically, what happens with benzoic acid is there's very strong hydrogen bonding interaction. So strong that it causes 2 benzoic acid molecules to couple like this. And you have a hydrogen bonding interaction here and a hydrogen bonding interaction here. And so what happens, this is especially noticeable in colligative properties. This is why it's in chapter 14. Colligative properties depends on how many independent particles there are in solution. It doesn't care about stoichiometric concentration or whatever. So I might make up a solution that's 1 mole in benzoic acid, but it's effectively going to behave like a half a mole. Why? Because originally I might have 1 mole of benzoic acid molecules, but if they pair up like this, and those pairs are very strong, then I effectively cut down the concentration, the particle concentration in the solution by half, which means its colligative properties are going to be way, way off from what you expect. And so this is ideal. I have 1 mole of benzoic acid molecules, but in reality, they behave effectively as half of that because they're all paired up. That's the difference between effective concentration and the other examples in chapter 6, ideal gas versus real gas. But if you go through this figure here, figure 1424, showing ion clusters, table 14.4, if you understand these, then you understand effective concentration versus stoichiometric concentration. And effective concentration here called the activity, which takes into account attractions, not just interionic, these aren't ions, just attractions. These attractions cause things to not behave independently and to pair up or form clusters versus stoichiometric concentration. And so if we're looking at, how reactive this is going to be a lot less reactive. If these are already tied up with one another, they're less capable of reacting with other species. So its activity goes down. The stoichiometric concentration would be 1 mole per whatever. Its effective concentration would be half a mole per whatever. That's this. And so it gets worse the more concentrated you get. So this is a table that I cover. I spend a lot of time on this table, M1A. I'm talking about this because if you don't have very many particles around, then they don't see each other. But if you have a lot of particles around, then they start seeing each other. And so if we have lead-2 nitrate should split up into 3 particles, lead-2 and 2 nitrates. And that's what it does when they're far enough apart, but you know, what happens is the ions see one another, and although they don't form an ionic bond and precipitate, for a moment they're attracted to one another and they don't behave independently. And so when we're at 10 to the minus 3 molal, 10 to the minus 3 molal, we're already seeing that like about 10% of these are paired up, you know, or clustered. And so the effective concentration is only 2.89, not 3. When we get all the way to 1, then it's behaving like 1.3 independent particles. You know, from 3, that's like 50%, more than 50% of them are tied up. Does that make sense? Does this table make sense? So you got to understand, when we have a table like this, what you should do is you should write little notes. You know, what's the main take-home message of this table? The main take-home message of this table is 2 things. One, this becomes more problematic with higher concentrations. You know, things don't behave independently. And 2, with higher charges. With lower charges, it's not as bad. You know, like sodium chloride is 1 mole, 2. It should be 2. It's 181. But at higher charges, like, you know, plus 2 here. Look at magnesium sulfate. This is plus 2 minus 2. This is plus 2 minus 1. And so plus 2 minus 1, it gets worse. For plus 2 minus 2, it's even worse. Why? Because of the ion attractions. These are ion attractions here. And so they show a little figure. The take-home message of this are we've got ion attractions causing things to not behave independently, to pair up or to cluster, meaning the effective concentration is going to be less. Is this going to be as reactive if they're all clustered like this? No, it's not going to be as reactive. And so its activity goes down. Now, we should be using activities for everything. I gave you an example of where activity impacts something. Where does it impact? It impacts pH calculations. This is why people have this misconception that pH only goes from 0 to 14 because they never do any calculations beyond 0 and 14. And the reason they don't do calculations beyond 0 and 14 has to do with you're not supposed to use stoichiometric concentrations. You should be using activities. So the errors in those calculations are going to be too big. If the errors are too big, then just ignore it. That's what they do in Chem 4. They just ignore it because they don't want to get into it in Chem 4. And so it's best to ignore those, you know, but you can't ignore those because, you know, as you go on, because, you know, it's like this. In Chem 4, they try to keep things, you know, it's like if you're in, as you progress, you know, you want to start off simple. You don't want too many, you know, if you're learning how to ride a bike, you don't want to ride on a busy street. You want to keep it simple, you know, and that's what they're trying to do. Keep it simple. But eventually you're going to, you know, have to maybe ride on a busy street. So you should be prepared to do that. And so this is like these calculations here, you know. We're not going to do that. You know, what are we doing with activities? We're doing nothing with activities. The only thing we're doing with activities is saying if the concentrations get high or there's strong attractions, maybe we should start thinking activities instead. What we're doing is we're saying the activities are approximately equal to the ideal. But that's going to fail. Eventually that's going to fail. So it's the same thing. You know, right now we're just saying that, you know, KEQ, you're right, KEQ is the activity of the products. Activity of G raised to the G, activity of H raised to the H, activity of A raised to the A, activity of B raised to the B. So what we're saying is that we're going to say that the activity of solids and liquids is equal to 1. Concentration really doesn't change. You know, its concentration really doesn't change. When we think about what's the concentration of pure water, concentration of pure water is 55.5 moles per liter. But yesterday we did the advanced calculation. The advanced calculation was, what if you squeeze the water down and compress its volume? If you squeeze the water down and compress its volume, then you're going to pack more water molecules in a liter. And so its concentration actually does change, but how much does it change by? It changes by very little. You know, so in last night's calculation, which you can watch on the video, some of you were there, but in last night's calculation, what we're saying is that from about 0 to 100 atmospheres, even if you squeeze it down, it doesn't really change the volume much. You know, liquids are incompressible. That's what you learn in Chem 4. You can't compress liquids. You can't compress solids. Well, you can compress liquids just a little bit. But if you go up to, that's from 0 to 100, or I think if you go up to 1,000 atmospheres or 1,000 bars, then you can put more squeeze, more pressure in there, and you can pack more water, and then you can change the concentration a little bit, and this activity changes. Does that make sense? So the activity, you know, it doesn't really change, you know, under normal conditions that we use, and so its activity is just one, basically. The activity of solutions, we just assume is going to be about equal to its stoichiometric concentration. We have to do the same thing for gases. For gases, we shouldn't be using the ideal pressure. We should be using the real pressure. And we should be calculating the real pressure using the Van Hoff equation or the Van der Waals equation or any of the other equations that are used for real gases. But, you know, is it really going to make that much of a difference? Not under the conditions we normally work with, you know, but at extremely high pressures, it will make a difference. And at extremely cold temperatures, it will make a difference because then gases tend to deviate from ideal behavior. So the activity of it is, we're assuming, is just its ideal pressure. And not, we're not going to use the Van der Waals equation. Do you remember the Van der Waals equation? In chapter 6. So essentially we should be doing the same thing for gases. Real gases. So we should be calculating the pressure based on this. This would be its effective pressure, not its ideal pressure, not the stoichiometric pressure, something like that. You know, and that's because why? Two reasons why. One is that gas particles aren't totally independent of one another. That lowers the pressure. And two, in an ideal gas, we assume zero volume. And so, you know, a lot of people ignore these figures. A lot of people ignore the tables. You shouldn't, because the figures in the tables kind of summarize a lot of the concepts. And so the gas particles themselves occupy space. So if you have 1 liter of gas, it's not truly 1 liter. You know, there's some space occupied by the particles themselves, and so you can have a little bit. We'll have a volume of empty space plus a volume of particles. And then that's kind of summarized in this table here. A is for the interactions between the particles. B is for the volume of particles. And so you can see the strongest interactions, the weakest interaction would be, of course, with ideal gases, we have no interaction. But on this table, the weakest is helium. Therefore, helium is the most ideal in terms of attractions between helium atoms. So helium is going to have the weakest attractions. Hydrogen is significantly more than helium. The worst on this table would be like propane. Propane is going to have much stronger interactions between the molecules. So propane is not going to behave so ideally. So helium, we could say helium's pretty ideal, and we're going to get very little error in our calculation. Propane, a lot less ideal, we're going to get more error. So if we're doing propane, then we should be thinking about that. And then for volumes, all these volumes are fairly small. So volume impact's only really going to occur at extremely high pressures. Yeah. And so this table shows this drop is due to the attractions. Hydrogen has very weak attractions here, and this rise is due to the volumes here. So I wanted you to review some of that stuff earlier so that activity would make more sense. Incorporating activities is not terribly difficult. Calculating van der Waals is not terribly difficult. To do that. But it's beyond the scope, so that's kind of next level, or next step up, where you do something like that. The book talked a lot about activity. So if you want to read more about it, read the start of chapter 15. I did it a different approach because they're doing it more from the theoretical. There are two ways we could derive the equilibrium law. One way is we could derive it theoretically. Here, this is the equation we end up with, theoretical derivation. The other way we can derive the equilibrium law, which is just K, the equilibrium constant expression, is by empirically, through observation. So historically it was done empirically, so that's all we did. I didn't want to get into the theoretical aspects of this yet, Okay, other questions? Go ahead. I'm sorry, what was the question? Who had the question? Did you have it, Andrew? No. Okay. No other questions? So we're going to continue with multi-equilibria or multi-steps equilibria here. And there are two types of calculations that we're often asked for acids. One is what is the pH in the acid? And two, what is the inventory? The inventory is just a listing of all species. Present. And equilibrium. And so the inventory, we have to do all the calculations. So, for example, if we have a triprotic acid like this, phosphoric acid, then the inventory, we need to know all the species that are present here, like H3PO4, and on. So we have Ka1, K2, K3. Ka1 deals with, did I already talk about this? The first proton coming off. And so the first hydrogen, this is the triprotic acid, so the first proton coming off from hydronium, that's 7.1 times 10 minus 3. And then we're left with dihydrogen phosphate. Dihydrogen phosphate is also an acid. It's a much weaker acid, but it can lose a hydronium or an H plus to water to form a hydronium. That's 10 to the minus 8. So we go from 10 to the minus 3 to 10 to the minus 8 is 5 orders of magnitude, which is about 100,000 times weaker here. And then we have monohydrogen phosphate. Monohydrogen phosphate is going to be the weakest of them all. Because when we look at the Ka for this one, it's 10 to the minus 13, which is another 100,000 times weaker than this one here. And so even though it's a triprotic acid, it gets successively weaker with each step. The first one's the strongest here. That has an impact on the pH. Oftentimes we might have a complicated acid like this, and if we want the pH, we want to know how much hydronium is present at equilibrium. Well, what we will do frequently is we'll just do step 1. That is, we do step 1, ignore step 2 and step 3, because step 2 isn't going to produce much, because it's much smaller, 10 to the minus 8. When we think about 10 to the minus 8, the last problem in the homework for chapter 15 is if you had a 10 to the minus 10, about how much reaction is at 10 to the minus 10. If we had a K of 10 to the minus 10, then the percent reaction is about 0.0001% reaction. That's 0.0001%. How much reaction is that? Very little. 10 to the minus 8 is also going to be very low. And in addition to that, we're going to have something called the common ion effect, which is going to make it even smaller. So the percent reaction is actually going to be quite a bit smaller due to the common ion effect, which we'll talk about. But we're going to go through these and do these calculations because all this comes from experience. So experience tells me that most likely I only have to do step 1 if I want the pH for a multi-protic acid like this. There's also one other contributor. If I think about this, pH, we want all hydronium contributors. And so pH is based on the total hydronium. And so what contributes hydronium to water? What contributes hydronium to water is Ka, and we could have multiple Kas. You know, if we only have a monoprotic acid, we only have one Ka, and that's Ka for that acid. And so we could have Kas and Kw. Kw is also going to contribute hydronium because we can't stop waters from colliding. And so there's actually a step 4 here. The step 4 is going to be Kw. Kw is water plus water yields hydronium plus hydroxide. So we're going to have 4 steps that contribute hydronium to these. But water is 10 to the minus 14. 10 to the minus 14, how much hydronium do we expect from water? Very little. And so it depends on how much hydronium we get from these previous steps, you know, how we deal with it. And so experience tells me if I'm only interested in pH, I usually do just step 1 because step 2 is minor. The only time I would do step 2 is if the K were significant. Now, what is a significant K? K that's significant would be like 10 to the minus 2. If I had a 10 to the minus 2 for this step, I would consider it. That means this has to be bigger than 10 to the minus 3. And so if Ka2 here were 10 to the minus 2, I would worry about it contributing. But this is 10 to the minus 8. I'm not going to worry too much about it. Okay, how do we know these things? Well, we've done the calculations and we see it. And so often what happens is the book's already done the calculations, they've seen it, but you haven't. And so what you're doing is you're just taking the book's word for it, which we don't always want to do, because if somebody says to justify your point, you can't say, well, you know, that's what I learned in the book. You know, the book said to skip it. And so what we look at are some examples here. Like, for example, if I was interested in the pH of hydrosulfuric acid, I know that Ka1 is going to be the biggest contributor because that's 10 to the minus 7. That's going to have the most percent reaction. And then I look at Ka2. Ka2 is 10 to the minus 19. But Kw is what? Kw is 10 to the minus 14. And so when I think about this hydrosulfuric acid, Ka1 is going to be the biggest contributor, followed by Kw. So step 1 would be Ka1. Step 2 would be Kw because Kw is bigger than Ka2. And so I'd have 3 steps. This one, Kw, and then Ka2 in succession, going from the biggest contributor of hydronium to the smallest. Now, when I think about this, step 1 is going to be the biggest because, you know, 10 to the minus 14 is 7 orders of magnitude smaller, so it's not going to be so significant. Let's look at carbonic acid. Ka1, yeah, but Ka2 is how many orders of magnitude smaller? That would be 4 orders of magnitude smaller. So most likely, you know, Ka1 is going to be the most significant. If I look at citric acid, I take a look at Ka1. Okay, Ka1 is going to be the biggest. It's going to contribute the most. Should I ignore Ka2 for citric acid? And here, in this case, I probably would not ignore it because look at this is 10 to the minus 4, this is 10 to the minus 5, they're really close. And so I'd expect Ka2 to be a significant contributor here, but maybe not Ka3 because there's one other thing that could complicate your assessment of these, and that's the common ion effect, which we'll talk about. Here, this should work nicely. Not only that, in this, for citric acid, here, I would worry about doing it stepwise versus doing it simultaneous. You know, in this case, I might have to do this simultaneously. Oxalic acid should work nicely. I mean, well, 3 orders of magnitude turns out to be okay. This one, no problem, sulfuric. Sulfuric, well, Ka1 for sure is going to be the most. But take a look at Ka2. K2 has a magnitude of 10 to the minus 2, which tells me I probably should worry about it because that's fairly big. And in fact, it is. It's big enough to add another 10% hydronium to this. And so these are based from experience. And where do we get this experience from? We get the experience from just doing some calculations and then kind of analyzing it. So let's just do this first calculation here. I'm going to use your book's example. We're going to look at it in more depth, and we're going to do both 1 and 2. This is what we did here. We're going to use 3.0 molar phosphoric acid. So 3.0 molar, that's, this is different. That's kind of high. Usually we don't, although it's not high, 3.0 molar is what we call dilute phosphoric acid. But the reason you don't see like 3 molar, 6 molar, 12 molar, 18 molar is, do you know why we don't see that much? Because if we're dealing with 6 molar, 18 molar, what do you think is going to happen? Can we use the stoichiometric concentration if we're dealing with 18 molar? Do you think? Or in other words, sometimes you should know some numbers. Or have some ballpark numbers. Molality and molarity are close. Where do we start seeing some significant deviations? This is like 1.0 molar, and we're already starting to see some significant deviations from ideal stoichiometric versus effective real. So one thing that throws up a alarm, this is 3 molar. That's even more concentrated than this. So I got to start thinking that, hey, wait a minute, maybe I shouldn't be using stoichiometric. Maybe I should be using activities. So why did they pick 3 molar for their example in the book? They picked 3 molar. You know why? 3 molar, they chose 3 molar so that the simplifying assumption would work, Because if they chose 1 molar, the simplifying assumption would fail. Or if they chose 2.5 molar, I think the simplifying assumption would fail. And so it's about 3 molar, and they don't want to go higher, because if you go higher, like if you go on 6 molar, or 10 molar, then the simplifying assumption would work quite well because, it's like if you take a drop of water out of a glass versus a drop of water out of an Olympic-sized swimming pool, which one's going to be more significant out of a glass, then which one's going to be less significant out of a swimming pool? So if we have, the bigger the concentration here, the more likely the simplifying assumption is going to work. That is, the more likely the change is going to be negligible. But anyway, we are not going to deal with it other than say that, we're aware of it and it could introduce errors into our calculation. But we're going to go with it. So when we look at the book's calculation here, they're doing 3.0 molar phosphoric acid. Now, I set up ice tables for everything, so we're just going to do this calculation, but we're going to do it some alternative analysis. So if I have something like this, and I want the pH only, then there's a good chance that all I have to do is step 1. And I don't have to do 2, 3, and 4. Good chance. If I want the inventory, that is all the species present at equilibrium, then I have to do all the steps. And so we're going to do the inventory. We're going to get everything present at equilibrium, and then we're going to take a look at pH. And so when we do this, this is acid plus water. And what we want is we want the biggest contributor to hydronium present. The biggest contributor to hydronium is going to have the largest K. And so we have 4 K values, K1, K2, K3, and KW. KW is 10 to the minus 14. And so we'll pick the biggest one here. That's going to be the largest contributor. And anyway, this is stepwise. So we've got to start off with phosphoric acid. That's what we have. And so we do Ka, which is phosphoric acid plus water. This is going to yield hydronium plus dihydrogen phosphate, H2PO from 1. Okay. Next, we'll just put in our initial, which is going to be 3.0 molar, H2O, 0 molar, and 0 molar. So we're going to assume that nothing's hydrolyzed yet. And then the change will be minus X molar, plus X molar, plus X molar. Okay. And so at equilibrium, we're going to have 3.0 minus X molar, X molar, and X molar. Ka1, this is Ka1 for phosphoric acid. Is going to equal 7.1 times 10 minus 3. Okay, so that's going to equal the hydronium concentration times the dihydrogen phosphate concentration divided by the phosphoric acid concentration. Water has an activity of 1, so we exclude it. Okay, then plug it in. We're going to get X squared divided by 3.0 minus X. Yeah, there's some ways of figuring out when the simplifying assumption is going to work, you know. When it's going to work is when you start off with a big initial, like 3. The bigger the initial, the better, because that would be like a larger and larger swimming pool of water. And a small x. The small x is going to come from K. K is 10 to the minus 3, so we don't expect that much forward reaction.
I thought you used the SA only when you preset the ice.
No, we use SA all the time. Yeah. The reason we use the reason we would do a reset here is if this were 10 to the positive 3. If this were 10 to the positive 3, I would reset at 1. Yeah, if it's 10 to the positive 3, it should be all products, very little reactant. And so in this case, this is backwards, you know. We look at what the downhill side is. And so over here, it's downhill on the reactant, uphill on the products. And so I don't expect much change, much to make it up the hill, you know, basically, because this favors, essentially this favors, just like 1,000 to 1, you know, 10 to the minus 3. But, you know, if this were 10 to the positive 3, then I'd have the opposite scenario. If this were 10 to the positive 3, this would be the reactants, this would be the product, and I'd expect it to be favored on the product side, but when I look at this, all my atoms are on the reactant side, so what's going to happen is if all my atoms are over here, they're all going to fall down.
Oh, wait, so if it's negative, it favors reactants, or it favors products?
Yeah, if it's negative, it favors the reactants. If it's positive, it favors the product. And so if this were 10 to the positive 3, I would reset this and then go backwards. And so in other words, I'd push all the atoms off and then figure out how few can make it up. Very few can make it up based on the Maxwell-Boltzmann distribution we talked about before. So here, I would just use a simplifying assumption. You know, there's tricks we can do to figure out if it's going to work or not, but it involves a calculation or estimate. So let's just try it and see what happens. So we get x squared, or 3.0, which means that x is going to equal what? Something like this. Is that what you guys got? Yeah. Okay. Then we have to validate this simplifying assumption by calculating the percent change. The percent change will be the change x over the initial 3.0. Sometimes the change is 2x, sometimes the change is 3x. So we have to multiply this by 2 or multiply this by 3. But in this case, it's just x. And so that's 0.1459 divided by the initial, which is 3.0. So I have this in my calculator still. I'll just divide it by 3 times 100%. And the percent change I get is 4.864, etc. percent. So now, do you see why they picked 3? I mean, if they picked 2.5, it would have failed. Or if they picked 2, it would have failed. We're right at the limit. So this is less than 5%. If it's less than 5%, we'll accept it. But just because it's less than 5% doesn't mean it's equally good. So for example, if we had a percent change that was like 0.4%, that would be much better. Or if we had a percent change that was 0.048%, that would be much better. And so the smaller the percent change, the better our calculation will be. In this case, you know, there's a trade-off here because, you know, how hard is the algebra here? And so this is pretty simple, you know, this is a simple quadratic. And so this is of concern because it's approaching the cutoff. And so if I'm like at 1%, 2%, 3%, 4%, 5%, I start to worry. Calculations isn't going to be good, but I compare it to the math. You know, if the math is like a cubic equation or 4th order, 5th order, 6th order polynomial, then this is way too much work. And then I'd say, I gladly accept a 4.9%, you know, at the limit. I'd gladly accept that. But in this case, the quadratic is not difficult. And so we, alternatively to this, we could have used the quadratic. And so let's go ahead and take a look at what that would have done. If we use the quadratic, of course we're going to get a better answer. We're going to get a better answer because we're not making this assumption here. And so, alternatively, try the quadratic. Now the quadratic is not difficult, especially if you have a quadratic and a cubic solver on your calculator, then it's pretty easy. And so what we'll do is we'll just get it in quadratic form. And so that's going to be x squared. Okay, and then we'll do this minus, so this will be plus 7.1 times 10 to the minus 3, and then 3 times that, so that's going to be 3 times 7 is 21, 21.3 times 10 to the minus 3 is equal to 0. So this wasn't hard, to get it into quadratic form. And then let's go ahead and calculate it using a quadratic calculator, which is allowed. I mean, the quadratic calculator is allowed, then that changes the things. And so A is 1, B is 7.1 times 10 to the minus 3. So I'll just do 0.0071, maybe 7.1 times 10 to the minus 3. And then C is negative 0.0213. Or I'll just do 21.3 e to the minus 3. Let's punch it in there. And let's calculate it. Oops. Negative sign here. Calculate it. 0.412438. Actually, 0.142438. So this is without simplifying assumption. This is with simplifying assumption. Take a look. We have 1424 here, and we have 1459 here. So what is the error in this calculation here? This is not the percent change. The percent change is not the percent error. And so the percent error is not this. This is just to get a gauge of how big the change was. It's not accurate, but it gives us a rough approximation of how big the change was, because this answer is not necessarily going to be accurate. And if we know it's big, then it wasn't such a great assumption. And so the percent error here is going to be this value. We'll just do it to 4 digits. 0.1459 minus this value, 0.1424, divided by this value. This is the true value, which is 0.1424. And so that's going to give us 35.0035. 0.0035 divided by 0.1424 times 100. 2.457%. 2.457% error. So if we're okay with this 2.5% error, then simplifying assumption is fine. But how hard was it to solve this? It wasn't hard if you have a calculator. If you had to do quadratic formula, then I do this. But if I don't have to do the quadratic formula and I have a quadratic solver, I do this. Why introduce 2.5% error? Right. 1, it's not so hard. Math is not so hard. And so even though this is justified, the math wasn't too difficult, so I might as well use the more accurate value. And I'm just going to not go with this. I'll just go with this. And the reason is that we're approaching the limit here. But I also do the same thing. I mean, if the percent change was like 1%, 2%, 3%, I'd still look, how hard is the math? If the math is not hard, then what will I do? Simplifying assumption. If the math is hard, then use the simplifying assumption. So let's go with this one instead. Here. Actually, we could calculate K based on both. So let's calculate the concentrations with the simplifying assumption and without the simplifying assumption. So the concentrations with the simplifying assumption, I'm going to get 3.0 minus x, which is 0.1459. I'm not going to carry out all the digits. Let's go with this. Should be adequate, I think. Or should I carry out all the digits? 59. How many digits were there? So that was 3 times 7.1.0071 divided by our square root. A lot of digits. Maybe we'll do overkill here. 1459.45. Carry that many digits out. And that should be an amount of error. And so this is going to be 2.95. 2.85 or 065. 55. Yeah. Okay, got it. X here is going to be 0.145945 more. Next here will be 0.145945. And so what does K come out to here? So there's going to be a little bit of rounding error, that's all right. 0.145945. And since I'm carrying so many extra digits, rounding error is not going to be that bad. Divided by 2.854055 equals. And so I end up with a K value of 7.463 times 10 to the negative 3. Is that what you guys get? Okay. And so it should be 7.1, right? And so that's about a 0.3 difference. Actually, it's a little bit more, 0.363 difference. And so let me calculate the percent error. It's 0.363 divided by 7.1 times 100. The K comes out to 5% error, 5.11% error. So if we did the simplifying assumption, and we're kind of at the limit, then we're going to get about 5% error. The rounding shouldn't have impacted this much because I carried so many extra digits. Yeah. Is that what you guys get? Okay. Now, without the simplifying assumption, what are the concentrations that we calculate? And so without the simplifying assumption, I'm going to get 3.0 minus 0.142438. 142438, which is going to be equal to 2.85762. And then over here, this is going to equal 0.142438 molar and 0.142438 molar. Okay, so let's calculate our K value based on that. So 0.142438 squared divided by 2.857562. And so in this case, I get a K value equal to 7.09996 times 10 to the minus 3. All right, let's do minus 7.1 times 10 to the minus 3 divided by 7.1 times 10 to the minus 3 times 100. Okay, the percent error here is 0.000524% error. So when the math is hard, the simplifying assumption is a lifesaver, right? But the simplifying assumption will introduce an error when you're getting to the limit here, you know. Like say if the percent change were like 0.1%, then there's no reason to do the quadratic because you get the same answer. Or smaller. So if the percent change were 0.1% and smaller, then I wouldn't have bothered. Because the answer I would have gotten from the simplifying assumption would have matched the answer I got from the quadratic. But when the percent change grows bigger and bigger, then I got to start worrying, you know, because do I want a 5% error? Because then I think, you know, if you get something like this, you start wondering, did I do the math wrong? Did I make an algebra mistake? What happened? You know, and you didn't do the math wrong, you know, it was just because of this. Versus if you have something like this, like a 555% error, not a 5% error, then I don't worry about it. Well, you know, if we rounded this, it rounds to 7.1. Well, those are things you think about when you're doing these calculations. You think about, you know, the benefit versus the, you know, there's a negative aspect of the simplifying assumption too, and that's introducing error. So what we're going to do is we're just going to leave this with, you know, since it wasn't hard with the quadratic solver, we're just going to use a more accurate value here. We'll just do it without the simplifying assumption. And so we're going to continue on the calculation this way. Okay, like I said, oftentimes when we're asked for the pH, the biggest hydronium contribution is going to come from step 1. So if I stopped here to calculate the pH, then I just take the negative log of this. Okay. And assume the subsequent steps aren't going to yield much additional hydronium. And so let's go ahead and figure out what the pH is here. That would be the negative log of this number, 0.142438, which is 0.84637. So if I stop here, the pH would be equal to 0.84637. So what we're going to do is we're going to see how much additional hydronium will I get from step 2, and if it changes the pH. Okay, step 1 is the biggest. The next biggest hydronium ion contributor will have a Ka value. 6.3 times 10 to the minus 8. That will be step 2. 10 to the minus 8 is pretty small. So this is going to be H2PO4 minus plus H2O liquid. It's going to give us hydronium plus HPO4 2 minus. This is Ka2 for phosphoric acid, which is equal to Ka for dihydrogen phosphate, which is equal to 6.3 times 10 to the minus 8. So what this is this is what we call common ion or common species problem. And that is, right here, the H3PO4 doesn't continue on to step 2. Do you see that? And so this is what we call the end of the line for H3PO4. Okay, it's not going to change from here, but the hydronium will change. We expect to add a little bit of hydronium, a little bit because it's 10 to the minus 8, to this. And so how much additional hydronium are we going to add to this? So what we're going to do is we're going to start with this hydronium. And so the amount of hydronium we're going to start with is 0.142438 more. And then, let's see, extra. And the dihydrogen, where's that hydronium coming from? That hydronium is coming from dihydrogen phosphate. Where did the dihydrogen phosphate come from? The dihydrogen phosphate came from step 1. And so from step 1, I'm going to have 0.142438 molar. And so this will be my initial from step 2. My initial from step 2 came from the final from step 1. Okay. H2O is pure liquid, and then we're going to assume nothing's happened yet. We're just taking these. Now the change is going to be to the right because this is 0 over here. So I'm going to get minus x plus x plus x. And so at equilibrium, I'm going to have 0.142438 minus x. So I'm going to lose some dihydrogen phosphate. In the process, I'm going to form some additional hydronium. I'm going to get 0.142438 plus x molar hydronium, and then x molar monohydrogen phosphate. Now, Ka2 for phosphoric acid or Ka for dihydrogen phosphate is just equal to the products of the reaction. So it's equal to the hydronium times the monohydrogen phosphate divided by the dihydrogen phosphate. And so this is going to equal 0.142438 plus x times x divided by 0.142438 minus x. All right, although the math doesn't seem so hard here. I could do the quadratic, but I automatically just go to the simplifying assumption. And if the percent change is small, then don't worry about it. And so here, we'll use a simplifying assumption. When I do the simplifying assumption, then this plus x drops out. So this is like adding a drop of water to a swimming pool. So I don't know if this is really a swimming pool. I'm just imagining it being a swimming pool here. So this is 0.142438. And this is going to be times x. Okay, and then this is like removing a drop from the swimming pool. In the last example, it was like removing 5% of the water out of the swimming pool. If you remove 5% of the water out of the swimming pool, is that significant? Yeah, that's significant. Okay. But here, we'll do 0.142438. Now, this is an interesting thing that happens with these. Step 2, take a look. This cancels, and then x is equal to Ka2, which is equal to 6.3 times 10 to the minus 8. Okay, so if x is equal to 6.3 times 10 to the minus 8, what was the percent change? So let's just justify this here. The percent change is going to be the change, which is x over initial. And so that's going to be 6.3 times 10 to the minus 8 over the initial 0.142438. So now we're checking, is this really a drop out of the swimming pool, or is it a more significant chunk coming out of the swimming pool or adding into the swimming pool times 100%. So let's see what it comes out to. And so we'll do that 6.3 times 10 to the minus 8 divided by 0.142438 times 100. Okay, when we look at this percent change, we'll look at that. Percent change is quadruple 0.4 zeros 442%, 229. Just do 44.22%. If you look at that percent change, that's minuscule. So this was really like a drop out of the swimming pool, right? Or a drop into the swimming pool. It really didn't make an impact. Therefore, I wouldn't even bother doing the quadratic, because if I did the quadratic, I'd get the same answer. But you're taking my word for it. You shouldn't take my word for it. We should just see it for ourselves, you know? And so let's go ahead and do the quadratic and then see if we would have gotten the same answer with the quadratic versus the simplified assumption. And I'm picking this one because this is not too difficult to get in quadratic form. And so, alternatively, if you do the quadratic, so if we do the quadratic, let's get this into quadratic form. We're going to have 6.3 times 10 to the minus 8 times 0.142438. What does that come out to? Six point 3 times 10 to the minus 8 times 0.142438 is 8.9 times 10 to the minus 9, 8.973. Let's just do this over here to try to minimize roundabout error. And then minus 6.3 times 10 to the minus 8x. Minus 6.3 times 10 to the minus 8x is equal to, so this is going to be x squared plus 0.142438x. X squared plus 0.142438x. Okay, then I'm going to add this to both sides. So let's get everything on the right side. X squared plus 0.142438. This is going to be 7 zeros. So 1, 2, 3, 4, 5, 6, 7, and then a 6, 3. X minus 8.9739 times 10 to the minus 9 is equal to 0. All right, so let's try the quadratic and see what we get. So Yeah, A is 1. B is, enter that in, 0.142438063. C is negative 8.97359. 8.97359 times 10 to the negative 9. Let's calculate that. And so I get an X value of 6.29949. X is equal to 6.29999 times 10 to the minus 8. Okay, let's compare this X value to the X value we calculated here. The X value we calculated here is 6.3 times 10 to the minus 8 using the simplifying assumption. And then using the quadratic formula, we got 6.2999 times 10 to the minus 8, which means, what's the percent error? The percent error would be 0.0000 quadruple 01 would be the difference. It's a quadruple 01 divided by the true value, which would be the 6.299, 6.2999 times 100. And so here, by using the simplifying assumption, this was an error by 0.000158% error. The error is so small. Not only is the error so small, we're not allowed this many sig figs. If we were to round this to the proper number of sig figs, what would it round to? 6.3. So there's no difference. And so in this particular calculation, there's no way I would have done the quadratic. Even though the quadratic was not difficult, this percent change was so small, I knew I was going to get the same answer. And so if you're getting percent change is less than 0.1%, then it's not even worth doing the quadratic because your answer is going to be good in the simplifying assumption. Okay, what I'm going to do is I'm going to just use this. So it wasn't worth doing this. So we'll just use this value here. So how much am I going to lose here? So this is going to equal 1, 2, 3, 4, 5, 6. So I'm going to get 0.1424379 937. So did I lose much? I went from 38 to 37,937. I barely lost any. How much did I gain over here? If I did the calculation correctly, I would gain 0.142438063. So I barely gained any extra here. I went from 1424.38 to 1424.38.063. 1, 2, 3, 4, 5, 6, 7. Yeah, that's right. And then the X is, I did gain significant amount here. That's going to equal 6.3 times 10 to the minus 8 molar. Yeah. Okay, let's double check our calculation by calculating K. So if we double check, it's going to be this the hydronium times the monhydrogen phosphate diamide plus dihydrogen phosphate. Let's do that here. So I'm going to go 0.14, 24, 38063 times 6.3 times 10 to the minus 8 divided by 0.142437937. And the K value I calculated is 6.3000005 times 10 to the minus 8. So, with a simplifying assumption, what's my percent error in the K? Minimal. You see, I barely have any. And so this is good. And so the simplifying assumption worked very well here. And it worked very well for two reasons. The two reasons it worked very well is because, one, K is quite small. And two, because of something called the common ion effect. The common ion effect is based on Le Chatelier's principle. The more product, the more hydronium I have here, the more it wants to shift to the left. So if I keep increasing the hydronium, the push is to the left, but I can't push this to the left because I have a zero here. But what's going to happen is it's going to inhibit the forward reaction. Versus if both of these were zero, so if I bring the hydronium to zero, then I'm going to get bigger change forward. Okay? And so this is called the common ion effect. The common ion effect inhibits the forward reaction. And that's going to help. In addition to this very small K, help justify the simplifying assumption. All right, so now when I calculated pH, was there a significant difference in the pH by going on to step 2? So how much extra hydronium did I add? I added 0.00000063 additional hydronium. Is that enough to change the pH? So let's go ahead and calculate the pH here. And so if I do the negative log of 0.142438063, and do you know what I get? I get a pH of 0.84. Actually, did I screw that calculation up? Let me try that one more time because my pH did change significantly, but I think this is very sensitive. So sometimes when I hit the button, it doesn't very quick. So I get a pH of 0.84637. No difference at all. So was it, if I'm only interested in the pH, was it worth doing step 2? I could have saved myself 5 minutes, And that's what you're going to see. You're going to see when we have scenarios like this, although, this is 5 orders of magnitude different. But even with 3 orders of magnitude and the common ion effect, it doesn't make that much difference. So this is why we say when we have like a multi-protic or even a monoprotic with KW, then if we only want the pH, we usually do step 1 unless Ka2 is significant. Ka2 is significant, like at 10 to the minus 2. That's when we worry about step 2. However, I'm not just interested in pH, I want the inventory as well. So if I want the inventory as well, then I have to move on because step 2 doesn't quite do the entire inventory. I have to go to step 3. Step 3 will be the monhydrogen phosphate now, hydrolyzing water, and that's going to be 4.2 times 10 to the minus 13, which is very small, but still, we're interested in all species, no matter how little we have of them present. And then after step 3, we've got to do KW. KW is 10 to the minus 14.
So in this question, if K1 was like 7.1 times 10 to the negative 7, then step 2 would still be significant.
Okay, yeah. If this were 10 to the minus 7 and this were 10 to the minus 8, then I'd worry about step 2. There's 2 reasons I'd worry about step 2. One, they're comparable, 10 to the minus 7, 10 to the minus 8. And so I'd expect it to be a significant contributor, even with the common 9 effect, but I'd still do the calculation to make sure. But the other reason is, if this one was 10 to the minus 7, this one 10 to the minus 8, I might have to worry that I have to solve this simultaneously. Because if both are significant contributors, then what's going to happen is I'm going to generate hydronium here, and then step 2 changes that. If it changes that, then it's going to perturb step 1, that is upset it. That is, if step 2 increases hydronium, Le Chatelier says that step 1 has to shift back. And then I run into the circular problem where I have to do those simultaneously. And so for citric acid, what we have to do, it also depends on the concentration, of it. Since these are stepwise, it would be more significant if these were 2 different acids. And so let me give you an example of that, because step 2 depends on step 1, how much I have there. It could be that, step 1, if it were 10 to the minus 7, it produces so little of this, and that little tiny bit goes to here, then it's not so significant. And so it depends on the magnitude. But the thing is, that all comes from experience, and the experience sometimes can trick you because these magnitudes can, it's difficult to see where it exactly transitions, so the best thing is just to calculate it, unless it's obviously one way or the other. So what we're going to be doing is we're going to be doing these calculations and then do a little bit of broad analysis. So step 3 is 4.2 times 10 to the minus 13. So let's go ahead and do that. Basically, I expect step 3 to contribute nothing as far as additional hydronium, nothing significant. But we'll see, because we're going to do the calculation. Step 3 is going to be the monohydrogen phosphate. Water is going to yield hydronium and phosphate. Ka3 for phosphoric acid, which is equal to Ka for monohydrogen phosphate, is 4.2. 10 minus 13. All right, does dihydrogen phosphate carry down into step 3? No. This is where dihydrogen phosphate stops. It doesn't continue down. But hydronium does. And so hydronium carries down into step 3. So this continues down. And does monohydrogen phosphate continue? Yeah, monohydrogen phosphate continues down to step 3. And it's going to enter here. The monohydrogen phosphate concentration is going to be 6.3 times 10 to the minus 8 molar. That comes from step 2. And the hydronium concentration is going to be 0.142438 063. And the phosphate concentration is going to be 0 because we assume that nothing's happened yet. No hydrolysis. And so now we're going to let hydrolysis occur, so we're going to lose some of the monohydrogen phosphate, and that's going to create some more hydronium. So this is going to be plus X. And so at equilibrium, we're going to have 6.3 times 10 to the minus 8 minus X. And we're going to gain a little bit of hydronium, I would suspect, 142438063 plus X. And we'll gain some phosphate, small. So let's see how much additional hydronium we get. This is going to equal the hydronium concentration times the phosphate concentration divided by the monohydrogen phosphate concentration. And so that's going to be 0.142438063 plus X times X divided by 6.3 times 10 to the minus 8 minus X. Now, when I look at the simplifying assumption here, I have two kind of different scenarios. If I look at the numerator has a pretty big initial, 0.142438. And then I look at my K is 10 to the negative 13, X is going to be small. And so in the first case, I'm adding like a drop to a swimming pool, or a drop of water to the ocean. Adding a drop of water to the ocean is not going to change its volume significantly. And so the simplifying assumption should work fine, I predict, for the numerator. But how about the denominator? Look at my initial now. My initial is 6.3 times 10 to the negative 8. 6.3 times 10 to the negative 8 is pretty small. This isn't what I'd call a swimming pool's worth of initial. This would be more like a glass. And so if I remove a drop from a glass, I might notice it. And so you could get fancy. One way you could get fancy is say, okay, I'm only going to do the simplifying assumption for the numerator. And that will make this go from a quadratic just to X, solving for X. So if I did the simplifying assumption just for the numerator, then I'm pretty sure that would work. However, I'm not sure it's going to work for the denominator, but who knows? So what we'll do is we'll just try it for both, because that's just a guess. My guess could be totally wrong. And so I'm going to use the simplifying assumption for both. And so that means the numerator is going to simplify to this, 0.142438 plus 63 plus X is just that, times X divided by 6.3 times 10 to the negative 8 minus X is just 6.3 times 10 to the negative 8. Okay, then let's solve for X. If I solve for X, X is going to equal 4.2 times 10 to the negative 13 times 6.3 times 10 to the negative 8. Divided by 0.142438063. And that gives me 1.8576 times 10 to the negative 19. 10 to the negative 19 is really small, right? So maybe the simplifying assumption will work for the bottom. So let's try to justify it based on the denominator, which is going to have a bigger percent change than the numerator. And so the change here is 1.8576 times 10 to the negative 19. And the initial is 6.3 times 10 to the negative 8. And I can already see it's going to work, because this is 10 to the negative 19 over 10 to the negative 8 would give us 10 to the negative 11 times 10 squared would give us 10 to the negative 9%. But let's go ahead and calculate the actual value. It's going to be 6.3 times 10 to the negative 8 times 100, which is going to give us a 0.36990 294%. And so what do you think of that? A really small percent. So I was worried about the denominator for nothing. And why is that? Because the common ion effect, there's already a bunch of hydronium here. It's going to inhibit the forward reaction. And this is so small. So expect very little bit of extra point. So in this case, there would be no reason to do the quadratic, because you're going to get exactly the same answer, pretty much. Quadratic or not quadratic. But let me make sure I did the calculation correctly. And so let's plug in this x value here in the concentration here. So let's figure out what the x values are that too. So what I'm going to do is I'm just going to write this in decimal form. So it's going to be 0.70, 2, 3, 4, 6, 7, 6, 3 minus 0.18 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 1, 8, 5, 7, 6. And so this is going to give me 0.0000000062. Okay, then let's count the nines. 1, 2, 3, 4, 5, 6, 7, 8, 9 nines. And then what? 8, 1, 4, 2, 4. Okay. And then I'm going to have this, which is going to equal 0.14243806 plus 0.18 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 1, 8, 5, 7, 6, 1, 4, 2, 4, 3, 8, 6, 3, 3, 6, 9 zeros. 1, 8, 5, 7, 6. And then the phosphate is just going to be 1.8576 times 10 to the minus 19 molar. Did we add much additional hydronium to this? No. Well, let me make sure I did the calculation correctly. So let's double check the K value here. Our K is going to equal this. Can you plug that into your calculator? Have you ever tried plugging this into your calculator? Okay. So 142438063, and then 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. Can you plug that into your calculator? No. Your calculator is going to have a certain limit to how many digits you can put in there. And then if you exceed that, your calculator is automatically going to round that. And so there's another reason for resetting. The other reason to reset is to avoid calculator rounding errors. What happens is, let's say I have 0.1 minus x, like this. This is just a side topic here. If I have 0.1 minus x, and I calculate what x is, and so this is equal to 0.1 minus 0.99999999999. How many digits does your calculator hold? Well, it used to hold 8 digits. Now modern calculators hold up to 10 digits. So let's do this. This is 5. This is more than 10. If this is more than 10, what's your calculator going to do to this number? It's going to round it. And you know what it's going to round it to? It's going to round it to 0.1. And then what you're going to do is you're going to calculate 0. So if you have a 0 here because the calculator round off, is your K going to check out? No, your K is not going to check out. Are we out of time? Oh, too slow. Okay. I didn't quite finish this. I'll need to talk about it, but let me just